Hi and welcome to this module that introduces reinforcement learning. So far we have been looking at popular models of machine learning such as supervised and unsupervised learning. So, supervised learning we looked at the classification and the regression problem, and in unsupervised learning we looked at clustering and frequent pattern, so on and so forth. And I have a question for you. So how did you learn to cycle? Was it supervised learning or was it unsupervised learning? Right? There is really no one telling you how you should cycle, right? I mean, how many pounds of pressure you should put with your left foot, and what angle you should be leaning, and so on and so forth, right? If you think of it as a supervised learning problem, that is how it should be, and it wasn't completely unsupervised, because it's not like you just watch people cycling and then figured out what the pattern that you should move in order to cycle, and then you just magically got on a cycle and started cycling, right? So, what was the crucial thing here, right? There was a trial and error component, right? So, you had to get on the cycle, right? So, you had to try things out yourself before you could learn how to cycle in an acceptable manner, right? So, you had some kind of feedback. It was not completely unsupervised, right? There will be somebody standing there, and if you learn to cycle as a kid, there was somebody standing there and clapping and saying, hey, great, good job, come on, go on, or something like that. And of course, falling down hurts, so you know that, right? So, there is some amount of trial and error component, and there is a feedback that you are getting from the environment. So, this kind of learning, where you are learning to control a system through the trial and error and minimal feedback, is essentially what reinforcement learning is, right? So, a mathematical formalization that captures this kind of learning is what we refer to as reinforcement learning. Right. So, in the RL framework, you typically think of a learning agent, right. So, we already looked at learning agents, like it could be the supervised learner or it could be an unsupervised agent. In this case, we have a reinforcement learning agent that learns from close interaction with an environment that is outside the control of the agent, right. The RL agent learns from close interaction with an environment. So, what do I mean by close interaction here is that the agent senses the state in which the environment is, right, and it takes an action which it then applies to the environment, which causes the state of the environment to change. So, thereby completing the interaction cycle. So, the agent senses what is the state of the environment. So, if it is a cycle, it is going to sense what angle is the cycle tilting in, right, what speed I am moving forward, right, and at what speed am I falling, and so on and so forth. All this constitute the state of the system, state of the environment, and the agent is going to take an appropriate action, which would be, okay, lean to the right or push down with your right leg, right, and then this action is then applied to the environment, and that in turn changes the state of the environment, right. So, the agent learns from such close interaction with the environment, and we typically assume that the environment is stochastic. So, every time you take an action, you are not going to get the same response from the environment. So, things could be slightly different, right. So, there might be a small stone in the road that you did not have the last time you went over this place, and therefore, what was a smooth ride could suddenly turn bumpy, and so on and so forth, right. I mean, so you know that cycling always has some amount of noise, and then you have to react to the noise. So, apart from this interaction, the mathematical abstraction also assumes that there is some kind of an evaluation signal that is available from the environment that gives you some measure of how well you are performing in this particular task, right. If you remember, we needed to have an evaluation measure for every task, and we are assuming that this comes in the form of some kind of a scalar evaluation from the environment. It could be somebody clapping and saying that, hey, you are doing well, or it could be falling down and getting hurt. So, all of this would be translated to some kind of a numeric scale, right. That is the mathematical abstraction that we make, right. So, the goal of the agent is to learn a policy which is kind of a mapping from the states that you sense to the actions that you apply, so as to maximize a measure of long term performance. So, I am not just interested in staying upright for the next 2 seconds, but I am really interested in getting from point A to point B. So, I have to make sure that I stay balanced throughout the entire duration of the ride. So, this is the basic idea behind the reinforcement learning problem. So, each reinforcement learning algorithm, the goal is to learn a policy that maximizes some measure of long term performance, right. So, there have been many successful applications of reinforcement learning. So some of the marquee applications come from the domain of game playing, like with many classical AI approaches. So, backgammon is a board game based on die rolls. If people are not familiar with backgammon, it is similar to the game Ludo, but it has also got a rich history. People have been playing it for several centuries, and there are even world championships in backgammon. And the world's best player of backgammon is actually a reinforcement learning engine. So, notice that I did not qualify it saying the world's best computer player or anything. So, it was the world's best player, and it managed to beat the world champion in backgammon over a tournament, right. And so, more recent vintage, so people have also gotten a reinforcement learning agent to play at video games, Atari video games from scratch. So, the input to the system were like pixels from the screens, right, and the output from the system were joystick controls, and they managed to play these games from scratch, right. And so, in autonomous agents like in robots and other autonomous agents, reinforcement learning is almost always the learning algorithm of choice. And so, in adaptive control, and one of the again very prominent success stories of reinforcement learning is this helicopter pilot that was initially trained by Andrew Ng at Berkeley and later at Stanford, where you trained a reinforcement learning algorithm to fly a helicopter and at near human level competence, right. And there are other applications where people have looked at applying it in combinatorial optimization problems, solving really hard optimization problems, and also in personalization and in adaptive systems like intelligent tutoring systems, right. And so, to wrap up this set of introductory modules, I just wanted to recap the different machine learning paradigms that we will be covering in the course. So, the first one we will be looking at is supervised learning, where we will be looking at learning an input output map. And so, the tasks that we look at here are classification, where the outputs that we are looking to predict are categorical outputs like yes or no or blue or red or by a computer or not by a computer. And the second supervised learning problem we look at is regression, where the output is a continuous output. And the second class of problems we look at are unsupervised learning problems, where we are interested in discovering patterns in the data, not necessarily in predicting a specific output. And the canonical tasks we look at here are clustering, where we are interested in finding cohesive groups in the data, and also association rules, where we are interested in finding frequently occurring patterns, right. And the third paradigm, which we will spend very little time on, is reinforcement learning, where you are interested in learning control or learning to control a system based on minimal feedback, right. So, from the next module onwards, we will start looking at taking a little bit more mathematically rigorous look at machine learning.